Right now, inside a massive cloud facility, millions of invisible data packets are racing between servers every fraction of a second. When engineers map out how all this data moves, they use a traditional geographic naming convention to describe the flow. In this topological map, traffic entering or exiting a data center from an external client is north-south traffic. Zooming in, internal servers constantly talk to each other, passing data laterally. This east-west traffic multiplies exponentially, heavily eclipsing the north-south flow. This internal density creates a specific set of engineering challenges. Why do modern applications require so much internal data exchange? And how does standard infrastructure avoid collapsing under the load? To understand how data centers survive this volume, we have to break down what exactly generates it, the specific mechanisms required to route it, and the strict security protocols needed to keep it contained. Operating a cloud facility today requires a focus on the internal lateral fabric rather than just the perimeter. A legacy monolithic application processes requests top to bottom inside a single server, but modern applications require a microservices architecture, shattered into separate containers. When an external packet strikes a front-end container, it instantly fires multiple east-west packets, querying adjacent logic tiers. Even outside of direct user requests, the database clusters supporting these services require constant background communication. They must talk to each other to handle load balancing, replication, and failover redundancy. These database nodes continuously synchronize their states. This generates a massive baseline of heavy internal traffic that runs 24/7, entirely independent of what the external users are doing. Because modern data centers use highly virtualized environments, dozens of these interacting virtual machines often reside on the exact same physical host hardware, driving up the internal lateral communication even further. By breaking a single application into dozens of specialized, highly distributed microservices, network engineers have directly caused an explosion in east-west traffic volume. Leaving this massive volume of lateral traffic unchecked creates an overwhelmed network, with critical server nodes immediately bottlenecking under the physical strain. This diagram illustrates the first layer of traffic management. A dedicated load balancer intercepts incoming lateral requests and distributes them evenly across available processing nodes, preventing any single machine from hitting maximum capacity. However, load balancing alone is a surface-level fix. Virtual machines are constantly spinning up and shutting down, and physical network switches and cables simply cannot be manually reconfigured fast enough to route traffic to new destinations. To handle shifting environments, engineers deploy software-defined networking, or SDN, placing a virtualized control overlay above the physical hardware. Traffic detaches from hardwired cables and maps onto logical routing paths governed by software. Because the routing is defined by software, these overlays instantly adapt to the creation or deletion of virtual machines. Traffic is optimized and redirected in real time, without a single engineer needing to adjust a physical cable. The network fabric itself becomes entirely elastic, capable of scaling and shifting at the exact same speed as the compute resources it supports. Without the software abstraction provided by SDN, the sheer density and volatility of lateral traffic would quickly crush the data center's physical routing hardware. While an elastic, frictionless internal network is great for performance, optimizing a system entirely for speed introduces a severe security vulnerability. Traditional network security relies on a castle and moat approach. This heavily guards the external north-south perimeter, but leaves the interior completely open and trusted. If a threat actor manages to bypass the perimeter and compromise a single low-priority container or virtual machine, they enter that trusted interior space. Once inside, an attacker uses lateral movement. They ride frictionless east-west channels, jumping from an infected node into sensitive databases. Traditional edge firewalls are blind to this internal traffic. The architectural response to this vulnerability is micro-segmentation. Instead of relying on a single perimeter wall, micro-segmentation applies strict zero-trust firewall policies directly to the individual virtual machines and workloads, treating every internal connection as potentially hostile. This creates localized quarantine zones. An infection in a low-level analytics container is physically isolated by software, completely unable to traverse the east-west fabric to access a secure payment database. Protecting a modern cloud environment requires accepting that the perimeter will eventually be breached and pivoting resources to strictly police the millions of lateral interactions happening inside. Zooming out, the scale of this operation becomes apparent. No human engineering team can manually manage security policies, SDN routing paths, and load balancers across tens of thousands of dynamic nodes. To manage this complexity, data centers rely on container orchestration systems like Kubernetes or Docker Swarm. These orchestrators function as the central nervous system of the cloud. They automatically deploy applications and natively configure the precise east-west communication pathways those applications need to function. As they spin up new services, they continuously enforce the software-defined networking routing rules and micro-segmentation boundaries we've outlined, ensuring the network remains both fluid and secure. But even with automation, engineers face a final critical challenge: visibility. With millions of automated lateral exchanges happening simultaneously, any monitoring blind spot can lead to system failure. Maintaining performance requires rigorous, continuous monitoring tools that track the health, latency, and availability of every single east-west data flow. By analyzing this internal traffic data, orchestration tools and engineers can dynamically reallocate compute resources, preemptively solving bottlenecks before they impact a user. The core architecture of a cloud platform has evolved past the edge of the network. Stability and security now depend on the precision of those millions of lateral interactions happening deep within the internal fabric.